Okay, so what I'm going to do is that I'm going to review some more of the questions. I mean, to go through some O-level question papers similar to the first two videos I've been doing in my in this channel and whatnot, like the math, the and math numbers and at math quadratic equations. I'm going to do some more. I'm not going to do a whole lot. I'm going to do at least some of them for which you can understand at least the bit we want. Okay, so here's a problem. Since 2025, I've noticed that for indices and surds, those things are completely removed from the syllabus. We only have logarithms now. However, we will need the basic knowledge of the indices and surds, indices mostly. So we will find some equations in which we still have to use the logarithmic expressions and whatnot. And I'm going to find some questions related to that today. Okay, so obviously because I'm using drawboard here, not PowerPoint, because PowerPoint is not that helpful when it comes to drawing and whatnot, and the tools that I need. I'm going to use a PDF editor for that. So also what I'm going to do is I'm going to um, copy paste, copy from a past paper some questions that I find, paste it here and then solve it here. That's the way I'm going to do it. All right. So let's get to it. Before that, however, let me review some of the things about indices and logarithms. There's not really a whole lot of things to review from here. The main thing we have to review are the rules of indices and logarithms. Okay, so let me just go through them very quickly. We got a to the power m times a to the power n equals to a to the power m plus n. A to the power m divided by a to the power n equals to a to the power m minus n. A to the power m times b to the power m equals to a b whole to the power m. A to the power m divided by b to the power m equals to a by b whole to the power m. So some follow-ups and whatnot based on the multiplication division sign for the first four. Number 5, we have a to the power b whole to the power c, so we get a to the power bc. Then we have a to the power 0 equals to 1, a to the power minus n equals to 1 by a to the power n, a to the power 1 equals to a to the power, no, just a to the power n by n equals to, no, not m by n, 1 by n. We get nth root of a, and here we have a to the power n by n is equals to nth root of a to the power m, and then we have a to the power minus m by n, which is just going to be reciprocal of a to the power m by n. It is exactly the same as 1 by nth root of a to the power m. Okay, n and m, n as in, you know, okay, never mind. Yeah, that neighbors end, and Microsoft's m, I mean m as in Microsoft, n as in neighbor, things like that. Things are quite hard to distinguish when it comes to subtitles and whatnot, but hopefully you can recognize from what I've written on the screen. That's for the indices. For the logarithms, I have log base a of b plus log base a of c equals to log base a of bc. Then we have log base a of b divided, no, not divided by, minus log base a of c. We get log base a of b by c. Then we have log base a of a equals to 1. Log base a of 1 equals to 0. Log base, I think I'm missing something. Yeah. Log base a of b to the power c, I get c log base a to the power b. Yeah, I missed that. But this is one very important rule of logarithm. It's quite helpful. Then we have a to the power log base a of b equals to b, which means that if I have a base and its log and the base is the same for the logarithm we use as its power for the base, then the base and the logarithmic one with the same base will be cancelled out. So these two can be cancelled out pretty easily, and we get b. So that's one thing. And then similarly, we have log base a of a to the power b. This equals to b as well. How? This one is pretty easy to derive. We know from this rule, if we take the power to the front, we get this thing, right? So we can take b log base a of a. And we know if this part and this part are exactly the same, we get 1. So we get b times 1 equals to b. So that's how we get b right here. Then we have two more rules. One of them is the base change rule. I mean base change as in the completely different base, not anything similar to what I'm going to show you here. Log base of b, none of these are going to be the bases. We get log base c of b divided by log base c of a. Last one is where we shift them by writing the reciprocal using the base change rule. The way I get this is by doing the following. Log base b of b divided by log base b of a. This thing is equal to 1. So I get 1 by log base b of a. So that's what I get. So that's basically all the rules that I got for indices and logarithms. And oh yeah, wait, I also have another rule, a very important rule when it comes to equations. In this case, if a to the power x equals to a to the power y, then a x equals to y. Similarly, if I have here, if log base a of x equals to log base a of y, then x equals to y. This is another rule. So yeah, this is mainly the rules that we have to deal with. I'm going to cover this first one right here. This is taken from a question paper, but yeah, this is one of the types here. This type shows how we can evaluate such simple index expressions to get a values of p and q. Really important, okay? I mean for the basics and whatnot. I mean for index derivation. Such things will come in Math D. I'm not sure about AMathExp right now, but this is what you can expect. So what I'm going to do is I'm going to, for the left-hand side, I'll write this whole thing, a to the power 4 by 3 and b to the power minus 2 by 5 whole to the power half. Because the second root here, I mean the square root here, shows that it's going to be half power divided by a to the power minus 1 by 3 b to the power 3 by 5. So therefore we get, I will have to cancel out 1 by 2 with each of them. So I get 4 by 3 times 1 by 2. This is basically the rule that we have, which is this one right here, which is that if one power exists, I mean, if a power is outside of another one as power, the powers get multiplied. Same thing goes for this one. So therefore, we get this thing divided by a to the power 1 minus 1 by 3, b to the power 3 by 5. So therefore, we get a to the power 2 by 3, b to the power 1 by 3. Sorry, not 1 by 3, 1 by 5. So therefore, divided by a to the power minus 1 by 3, b to the power 3 by 5. Now, I'm going to do the following. Minus 2 by 5, this is going to be minus 1 by 5. And I'm going to get a to the power 2 by 3 plus 1 by 3. This minus becomes a plus. If we shift this upwards, this becomes a plus. Just from the power rule here, this one, that if this thing was a positive here, if we take it towards the top, the same way as in the power becomes negative. In the same way, if it was negative here, it goes to the top and becomes positive. So that's what I'm going to do. B to the power minus 1 by 5 minus 3 by 5. So therefore we get a to the power 1, b to the power minus 4 by 5. Okay, so p equals to 1, q equals to minus 4 by 5. Next, now I would solve this equation here, but the problem is that I want to show some more types of indices first of all. Then I'm going to come back to this. This is also a part of indices, but that's another type. Is we're solving different equations we have. But first of all, I want to solve different expressions. Here's another question. This one is very similar. Now, there's not a whole lot of questions of these sort of types here. So they're mostly the equation types. So let me solve this one for you. This one involves a whole lot of the use of indices I've shown you from their rules. So this one has to be 9p square cube whole to the power half times r to the power minus 3 divided by 2 cube times p cube, 2 cube p cube, q to the power minus 1, r to the power 1/5. So I get 3 because cube root of 9 is 3, p q to the power half, r to the power minus 3 divided by 8. P cube q to the power minus 1, r to the power 1/5. So we get uh, k, right? So k is going to be 3 by 8, p to the power 1 minus 3, q to the power half plus 1, r to the power 1 minus 3 minus 1/5. So therefore, we get 3/8 p to the power minus 2, q to the power 3 by 2, r to the power minus 16 by 5. So k equals to 3/8, p equals to minus 2, q equals to 3 by 2, r equals to minus 16 by 5. So this is another type of question that can come from indices part. However, really the most common types of question that can come from your indices part is the equation solving, whether that be using substitutions or regular equation solving or simultaneous equation. Still, indices solving is really important. I'm going to search some questions. In fact, I actually do have one printed right now, which is this one. So in this case, we have to use the understanding of the cubes and squares. So we need to have the knowledge of, at least if it is non-calculator, we have to know about things like squares of at least first 15 numbers and the cubes of at least first 5 numbers and 10. All right. So let me show you how this works. This thing can be written as 2 to the power 4 whole to the power 3x minus 2. And here we have 2 cube whole to the power 2x. The trick behind it is that we want to keep the base right here same as possible. If the base is same, we can go back to the earlier rule, which is this one right here. If a to the power x equals to a to the power y, then x equals to y. So therefore, we get the following. We get 2 to the power 12x minus 8 equals to the power 6x. So therefore, if these two are same, we can write as follows. The powers are going to be same, equal. So we get 6x equals to 8, 8 equals to 8 by 6. Okay, so this is one thing we get. Let me show you another question here. For this case, this is where you have to use the substitution technique. Substitution as in, I mean, obviously it's going to be pretty hard if you try to solve it this way, but the one that I showed you above was one of the ways. This one right here. Let me cover all the ways that I can actually solve the equation separately as important questions from O-level past papers for indices actually. So from here, I can actually do the following. If I have 2 to the power 6x, we know about the rules. 2 to the power 3x times 2, I can actually write this 2 as a power outside of this thing. So I can write this thing as 2 to the power 3x whole square minus 3 to the power 3x minus 5 equal to 0. But here's the thing. Would you want to write this e to the power 3x many times? We technically got a quadratic equation we can solve with e to the power 3x as our main required variable. So in this case, what we're going to do is that we're going to do the following. Okay, so I'm going to write 2e to the power 3x. I mean, this e to the power 3x be equal to y. The reason we do that is because now it's going to be a lot easier to solve this equation. So we get 2y squared minus 5y plus 2y minus 5 equal to 0. 2y, y minus 5 plus 1, y minus 5. Actually, not 2y, it's actually going to be just y to 2y minus 5. And here we get 1, 2y minus 5 equals 0. So we get 2y minus 5, y plus 1 equal to 0. From there, we get y equals to 5 by 2, y equals to minus 1. Now, here's a problem. I need to find out x, not y. So from this earlier expression, you have to equate y with that here to get this thing or this thing. Now, here's another problem. I realized that if you try to do power of anything and I mean things like this index form, our answer will never be negative. It is always going to be positive and greater than 0. So it cannot be anything even 0. So that's how we represent this in the exponential graph. It tries to touch the x-axis where y equal to 0, but it just never does that. So the x-axis just becomes asymptote. It means that this thing goes closer to 0, but it can never be 0. The value of anything with this power. Anything, not just e, anything. So that's one thing. Now, here's another trick. Similar, so if that's the case, then obviously this is not going to be the answer. But in this case, you'll notice that obviously we cannot have anything that is going to be e to the power, right? If, for example, if you have something like this, 2 to the power 5x equals to 32, I can easily say 2 to the power 5x equals to 2 to the power 5, 5x equals to 5, x equals to 1, right? However, here's a problem. In this case, I cannot do that because it can only be happening if we can somehow get same base on both sides of the equation in a single term so that we can actually equate the powers. In this case, we do not have any sort of base set here or anything that can form e, right? So the thing we can do is that we can apply logarithms on the left on both sides. But here's another thing. The trick behind doing this properly is to ensure that the logarithmic base that you choose is exactly the same as this index base. So you have to select log base e here. So we try to write log base e as ln. So in this case, you have to select ln e to the power 3x equals to ln to the ln of 5 by 2. And this is exactly the same reverse formula of the one that I showed you earlier, this one. Which is this one, where if the in the logarithmic expression this part is exactly the same while the base is the same, and if these parts are different while the base is the same, then the parts inside will be equal, x equal to y. That's what I try to show here. So that's one thing, and therefore I get 3x equals to ln 5 by 2, x equals to ln 5 by 2 divided by 3. This is the answer. And here's another thing. It says your exact solution. It means that you are supposed to include this logarithmic term definitely. However, in case it says two significant figures, one significant figures, you have to use a calculator. All right. In those cases, you definitely have to use a calculator. Anyways, another question that follows it is this one. So in this case, I notice that you have a simultaneous equation, two variables. Now, the first, I mean, this one can be solved entirely in digits alone. But in the first case, we have to keep the x and y alone without this e's here and whatnot. That's the variable thing we need to declude from here. So from equation one, we need to cancel out, we need to eliminate these e's here. So we get e to the power 4x minus 7 minus of this thing, because we know from here that if the bases are exactly the same and we divide, the powers are subtracted. And here, if this is positive, we try to bring the base and power upwards, this thing becomes negative power. So therefore, e to the power 4x minus 7 minus, no, yeah, 5x minus 7y equals e to the power minus 2. We get e to the power minus x minus 7y minus 7 equals e to the power minus 2. Now, because the bases are same, but the powers are different, we can just assume that powers are same. So minus x minus 7y minus 7 equals to minus 2. X plus 7y plus 7 equals to 2. So x plus 7y equals to minus 5. Equation 1. But actually, I can actually make a substitute here. I can actually take, okay, never mind, it's not going to be worth it. From equation 2, I actually take x comma, I mean x is a subject. So we can write this thing as 18 by y plus 7y equals to minus 5. So therefore we get minus 18 plus 7y square equals to minus 5y. So we get 7y square minus 5 plus 5y minus 18 equal to 0. So therefore we get 7 times 18. However, from here, we need to get 5, right? So I need to check a bit. Just a second. So I get 2 as 9 here. Not that's not the way. 16 minus 2, no. 14 minus 9, yeah. So I can do 7y square plus 14y minus 9y minus 18 equal to 0. So I get 7y, y plus 2 minus 9, y plus 2 equal to 0, y plus 2, 7y minus 9 equal to 0. I get y equals to minus 2, y equals to 9 by 7. And from here, I get the following. Okay, there should not be any problem because the powers can still definitely be minus. Then if you go back to the first equation, x equals to minus 18 by minus 2, y equals to minus 18 by 9 by 7, and then I get x equals to 9 and x equals to minus 18 times 7 by 9. So we get x equals to minus 14. So therefore, the solutions are going to be minus 14, minus 18, and 9, and minus 2. There you go. So that's the way you do it. Let me show you another math from here with a very similar type, if possible, or I'm going to also show another word of a logarithm. Logarithms are more common nowadays compared to indices. So let me just move on to logarithm. And then I'm going to show you logarithmic equations. So now I'm going to show you a logarithmic math. Although the first part definitely included logarithm, it wasn't that exciting. So I need to include another logarithmic math in which you have to definitely involve these logarithms. So there we go. Okay, so for this one, this is a logarithmic question. In here, I like to do the logarithm, first of all, expressions and stuff, then I'm going to move on to equations. So in this case, I have single logarithm to base 10. Now, log of base 10 of something can be written as LG of something or log of something, right? In Cambridge, we usually write this thing as LG, but internationally it is recognized as log. if we not involve any extra base here. So I write this thing like this, LG. So here I write as a single logarithm, right? So one thing I should realize is that I can move these two outwards first of all, and then I can have it do its thing. Because if we do 2 outwards, then we'll get 2 times 1 by 2 with the 2's cancelled, so we get 1, and that's what I've done here. Now what I'm going to do is I'm going to do the following. We have learned one formula, this one. Log base a of a equals to 1. It means that if this base and the inner portion are exactly the same, as in, yeah, so basically what we can do is that we can say that this equals to 1. So the base has to be exactly the same as this portion right here. So in that case, I have 3 LG10 plus 2 LGA minus LG 4B. Because this thing is exactly the same as 3 times 1, I can write 1 as LG10. And because of this, I now be able to write all three of these in the form of single logarithm. Not yet, actually. I realized that this thing has to be dealt with, the parts outside the logarithm. So now we need to do the following. LG 10 to the power 3 plus LGA square minus LG4B. So therefore we get LG 1000 plus LGA square minus LG4B. So therefore we get LG 10,000 A square divided by 4B. So therefore we get LG 500 A square divided by 2B. So that's going to be the answer. Similarly, I have another question here similar to this, which is going to be a part of your equations and stuff, logarithmic equations. Now, if you have expressions you're usually meant to write down in that way, let's say single logarithm and whatnot. I wish I could have found some other questions based on this, but it is what it is. So for this one, I can write this whole thing as follows. In this case, I have to use the base change rule. So I get this equals to 2 log base C of 3 equals to, not actually C of 3, I just want to write this thing as C here so that I can, if I have something like this, log base C of A, no, log base A of C equals to B, I can just write C equals to A to the power B. So I'm going to write this thing as follows, 2 by log base C of C. So I just use a base change rule to shift the powers, to shift the bases and this one. Now, just for ease, I realize that if I put this there, I'll get a quadratic expression again. So I'll just do let log base C of C equals to y, not y. Let me just do a because we have C here. Not even a because we have a here. So we get 2 by y equals to 7 plus 4y. 2 equals to 7y plus 4y square. So therefore we get 4y square minus plus 7y minus 2 equal to 0. So we get 4y square plus 8y minus y minus 2 equal to 0. 4y, y plus 8, sorry, y plus 2 minus 1, y plus 2 equal to 0. Y plus 2, 4y minus 1 equal to 0. So y equals to minus 2, 4y minus 1, 4y minus 1 equal to 0. So y equals to 1/4. But here's another thing. You should be able to realize that I have this thing equals to that. So, okay. So y equals to minus 2, y equals to 1/4. So log base 3 of c equals to minus 2, log base 3 of c equals to 1/4. So we get c equals to 3 to the power minus 2. C equals to 3 to the power 1/4. Let me just check the answer. Okay. Yeah. So this is one and this is another one. So C equals to 1/9 or C equals to that. That's going to be the final answer. Now, similarly, let me show you another question. Now I think I'm free to show some more questions from different parts of logarithms and indices as well. But I'm going to mostly focus on logarithms because logarithm is now something only, it's mostly focused on since 2025 because indices and surds are not that much focused on. At least they say that this is something called assumed knowledge. So for this one, we need to understand that if for this thing to exist, if you look at the curve of it, we realize that it only exists from the case that x is greater than 0. Generally for LG thing. So if this thing is 0, this will not exist. It has to be even, let's say 0.00001, right? So if that's the case, this 5x minus 3 must be greater than 0. So x is greater than 3/5. So that's the answer. So we get this question right now. In this case, okay, that looks pretty big. So for this one, I write this thing as follows. Because I noticed that this is LG, I can just write the following. LG, LG of 5x minus 3 equals to LG 10. So therefore, 5x minus 3 equals to 10, 5x equals to 13, x equals to 13/5. All right. Similarly, there is another question, or similarly, just quite another one. So we notice that is going to be log base y of x equals to 4 plus half log base y of 64 plus log base y of 162. Now here's another problem. Now the trick behind this one is that I want to keep every single terms with this little y right here, which I wanted to deal with on the left hand side. So what I'm going to do is that I'm going to do that. So I get log base y of x minus half log base y of 64 minus log base y of 162 equals to 4. So log base y of half log base y of 64 I can write as follows. I can write log base y of 64 to the power half. 64 to the power half can be written as square root of 64, which is going to be 8. So log base y of 8 minus log base y of 162 equals to 4. So I get log base y of x by 8 into 162. It is going to be 1286. Is equals to 4. Sorry, of that. Now, one thing I really want to do as well is that I want to make the following. 1 by log base x by 1286 of y equals to 4. The reason I do that is because I want to keep this y as is, and as I mentioned earlier, the method I've shown you is going to be exactly easier. So this means that if I shift this around, this means it is also going to be reciprocated if I keep this as a numerator. So I get log base x by 1286 of y equals to 1/4. So therefore, y equals to x by 1286 to the power 1/4. So therefore, fourth root of 1286 is something I need to find on the calculator. Hmm, that's weird. Okay, so I get some weird answer here, which I need to find out using the marks key. Okay, never mind. Actually, I made a calculation error. This is going to be 1296. So it's going to be 1296. So if I do 1296, then I'm going to get 6. So I get expression for y, which is going to be 4th root of x divided by 6. Now I got expression for y in terms of x here, so I get this expression as my final answer. So let's move on. Okay, so now let me show you a pretty big logarithmic question here, which is going to be from the following paper, which I have to search from my repository. 2017, February, March. So I'm just loading an ITCC question paper right now, but things are almost exactly similar. This should be, I mean, something similar does also exist in the May, June, and October, November paper part. This part contains a big kahuna, as in this part contains mostly the indices and logarithm. All right. So here's one of them. Now, if all your papers are not enough for practice, you can actually try the IDTC papers because you have a whole new queue of papers to practice from. So we know that cube root of -8 is going to become -2. Negative is not going to be a big deal when it comes to cube roots because it is nothing like a square root or something. So I get cube root of -8 is going to be -2 x to the power 9 whole to the power 1/3. And then we have x to the power -1 -3 whole to the power 1/6. So therefore we get -2x cubed times x to the power -3 by 6, which is going to be -2 by x cubed, no, -2x cubed x to the power -1 by 2. So I get -5 by 2 as the answer. That's going to be this one. So A is -2 and B is going to be 5 by 2. Another question. Now from here, I want to solve another question, another thing. If this thing is equal to 60 to 50, then I would like to find out what the value of x is. So it means that this thing is equal to -2 by x to the power 5 by 2 equals to -60 to 50. So x to the power 5 by 2 equals to 60 to 50 by 2, which is going to be 3125. So therefore, x equals to 3125 whole to the power 2 by 5. The way I recognize this one is by doing the following. If I power whole to the power 2 by 5 on both sides, I can actually cancel out the powers. I mean, cancel out these two. Look at one. So this equals to that. X equals to fifth root of 3125 whole square. So if I do the fifth root of 3125, I get 25 as my answer for value of x. Similarly, if I have another question, this one, in this case, I'm going to find out the following. Explain why x must be greater than 0.75. Here's a problem. If x was greater than 0, if x was 0.75, then 4x minus 3 will have to be 4 by 3 by 4 minus 3 equals to 0. So log base a of 0 is not possible. So this is why we can get such explanation. If you have something like x is greater than 0.75 for such expressions like this, the one thing you can do is by substituting this thing onto this inner portion right here. You'll realize that if it is equal to 0, then it's not going to be the case. It has to be anything greater than that. So this is the thing. So that y can be written as follows. So I need to take 2 pages here. Y can be written as that. So it means that y equals to log base a of ax plus 2 log base a of 4x minus 3 minus 1. So this is only possible if the bases and the inner portion are same. So I'm going to do that so that I can deal with things a lot easier. And then I have 4x minus 3 whole square because I did this as a power log base a of a. Then now we have log base a of ax times 4x minus 3 whole square divided by a. A's cancel out. So therefore we get log base a of x into 4x minus 3 whole square. Yeah, right. So therefore I can write log base a of x times this thing whole square. So I get 16x square minus 24x plus 9. So therefore I get log base a of 16x cubed minus 24x squared plus 9x. That's going to be the final answer. So that's going to be shown. Next up, I have this value. I mean the last part. The last part says as follows, although I need to, it's pretty hard to understand why it scrolls down, space down to the bottom of the page. But once I do this part, then I'll be set. So therefore, y equals to log base a of 9x. So it means that according to the question, this portion must be equal to that. So 16x cubed minus 24x squared plus 9x equals to 9x. So therefore I get 16x cubed minus 24x squared equal to 0. So I get x 16x squared minus 24 equal to 0. Now here's another problem. According to the question, x must be greater than 0.75. I mean, according to the statement earlier, right? So if that's the case, then I can easily say that x equal to 0. Had this been an option, this is not acceptable. On the other hand, if I have 16x squared minus 24 equal to 0, and I this thing as 16x squared equals to 24, this thing is going to be 2, this is going to be 3, x squared equals to 3 by 2, x equals to root 3 by 2. Negative is also not possible. So we get 3 by 2. We get x equals to 1.22. Let me show you another question, another helpful one, an important one, where we have an equation with two different logarithmic terms, but with both different bases. Okay, logarithms have different bases. So that's going to be of the following. Okay, that's not a big deal. But the thing is that this thing has a bit of an unusual stuff. Main thing is that the bases are different. All right. If the bases are different, we need to make them same. Is in the base change rule. And how do we do that? We know that obviously the bases are both powers of 5. So I can write this thing as log base 5 of root x equals to log base 5 of x divided by log base 5 of 25 equals to 3. So we get log base 5 of root x plus log base 5 of x divided by 2 equals to 3. Now, right away, you may just do the following. X is exactly the same as root x whole square. So I can easily say this thing is going to be log base of root x whole square. Let log base 5 of root x equals to y and solve the equation. All right. Otherwise, we can do the following. I can say this thing x to the power 5 with x to the power half can be put together at the front to get half log base 5 to the power x plus log base 5 to the power x divided by 2 equals to 3. These two are same, right? So we can easily say the following. Log base 5 of x equals to 3. If this is the case, I can directly say x equals to 5 cubed, x equals to 125. Yeah. So x equals to 125 according to what I have found here as my answer. Now, that is one thing you can do. Another thing is that although that's going to be lengthier, although I may try to do that, I'll actually do the alternative method here. So I did not realize this until the end of that math solving part that the second method that I did there is completely wrong. Okay, the first method I did there is completely correct, but the second method I did not realize until the end, obviously, that this root x whole square only applies for the part after the base, not the entire logarithm. So in that case, I cannot just let this entire logarithm be something. Okay, so definitely I cannot say that root x here is something and then I can substitute to whole square and whatnot. So yeah, I did not realize that it was a mistake until the end. So keep on watching this part and you'll realize it yourself as well. Okay. So keeping this portion as is, we get log base 5 of root x plus log base 5 of root x whole square divided by 2 equals to 3. Next, I can write this thing as following. Let log base 5 of root x be y. If that's the case, then we can write log y equals to y square by 2 equals 3. So I get 2y plus y square equals to 3, y square plus 2y minus 3 equal to 0. So I get y square plus 3y minus 3 equal to 0. So I get y plus 3 minus 1, y plus 3 equal to 0. Not y plus 3, never mind. Not y plus 3 is 2y and then there's 3 there. Y square plus 2y minus 3 equal to 0. 2y, actually, this is going to be 6. If this is 6, then this just becomes y square plus 3y. This is 6. So I get y square plus 3y. What have I done? So y square plus 2y minus 6 equal to 0. So it means that I can. So you can clearly see that I was endlessly trying to find different methods and whatnot to solve this equation alone, even using the quadratic formula. But then I realized that it just doesn't work. Okay, when I realized that the quadratic equation is not insolvable, even despite getting the correct integer answers in the other method I showed earlier, it just doesn't work. I mean, you can see it for yourself. Okay, I thought I would be able to do it this way, but for some reason, I cannot seem to get my answer. And it was when I realized that I did it completely wrong. Just look at this. Yeah, actually, I understood why. This thing is not the same as what you expect. Okay, so this is something you cannot do. Now, I was actually doing this way to actually show you this is some mistake someone can do. Okay, so keep in mind when you do such sort of thing. This will be a mistake if you do such sort of thing. This is a real, actual easy assumption what many people will try to do. Assuming this thing, if you get something like this for some reason, you may assume this to be a substitution. However, it's not going to be correct. So this is going to be completely incorrect. So this is completely incorrect. Anyways, if that's the case, let me show you another math. In fact, not another math. This is the last math I'm going to do. Actually, this paper, the one that I found right now, actually has two questions, one from indices and one from logarithms, simultaneous equation. I think that's the better way to end this part. So let me just show you what I got. This is the one. This one includes one of them with one power of something, another one with another power of something. This one is power of 3. This one is power of 2. So now for the equation 1, I get 3 to the power x times 3 to the power 2 whole to the power y minus 1. 243, if you don't know, is 3 to the power 5. So therefore, we get 3 to the power x times 3 to the power 2y minus 2 equals to 3 to the power 5. Therefore, 3 to the power x plus 2y minus 2 equals to 3 to the power 5. X plus 2y minus 2 equals to 5. X plus 2y equals to 7. This is equation 3. And for the second equation, 8 times 2 to the power y minus half equals to 2 to the power 2x plus 1 divided by 4 root. Okay, that's a bit complex. So I'm going to write this thing as 2 cube times 2 to the power y minus half equals to 2 to the power 2x plus 1 divided by 2 square times 2 to the power half. So therefore, I get 2 to the power 3 times 2 to the power y minus half. This equals to 2 to the power 2x plus 1 divided by 2 to the power 2 plus half. It is going to be 5 by 2. So therefore, I get 2 to the power 3 plus y minus half. So I need to add them together again. I get then 2 to the power this thing minus that. Okay, now I'm going to equate the powers together. So I get 3 plus y equals to 2x plus 1 minus, oh wait, have I not erased that? There you go. 3 plus y minus half equals to 2x plus 1 minus 5 by 2. So therefore I get 2x, because there's that there, I get 5 by 2 minus half minus 1 plus 3 equals to 2x minus y minus 1 minus 1 plus 3. So now I get to do the following. 2x minus y equals to 5 by 2 minus half is going to be 4 by 2. 4 by 2 is going to be that, then 2. 2 plus 3 is 5. 5 minus 1 is 4. So I get 2x minus y equals to 4. Equation 4. So now I need to do equation 3 plus equation 4 times 2 so that I can eliminate y. X plus 2y equal to 7. And 2x, not 2x, x plus 2y equal to 7. 4x minus 2y equals to 4. Not 4, 8. So therefore, I get 15, 5x equals to 15, x equals to 3. And if I substitute this to, let's say, fourth equation, I get 2 to the 2 times 3 minus y equals to 4. 6 minus y equals to 4, y equals to 2. Now, we get xy equals to 3 comma 2. Now the better way to deal with this is by checking if this thing is substituting or actually fits well there. We get x equal to 3 and y equals to 2. Okay, so we get x equals to 3 and y equals to 2. So let me just do a bit of check here. 3 cube times 9 to the power 2 minus 1. So we get 9. So we get here 27 times 9 is going to be 243. That's okay. And in this case, I have 8 times 2y. Okay. Then we have 2 to the power 6 plus 1. Okay, I think this is a bit hard to substitute, satisfy. But because one of them is satisfied properly, I think there's no need to satisfy the other. Or in fact, I think it's better to do that. This is 2 to the power 6 plus 1. So we get 2 to the power 7 divided by 4 root 2. So we get 2 cube times 5 by 2. So we get 11 by 2. And here we get 2 to the power 7 divided by 2 square times, no, 2 square plus half. So 2 to the power 11 by 2 equals 2 to the power 7 minus 2, it is 5. 5 minus half, it is going to be 5 minus half. Okay, that's not going to be good. 2 minus half. Yeah, that's 3 by 2, not 5 by 2. So that's 3 by 2. So therefore, we get 2 cube. 3 plus 3 by 2 is going to be 9 by 2. So therefore, we get 2 to the power 9 by 2. That's not better. So this is something I did on the other hand. No need to care about that, but that is just to check if it satisfies. Similar, I mean, coincidentally, I have another question here, which is of logarithms. But this one is not your average logarithm. This is something which will form a cubic equation. So it's a bit hectic. I mean, lengthier. So in this case, I need to make sure that I can put the logarithm on the left-hand side because I also have a non-logarithmic term here. So for this case, I can write log base 2 of y plus 1 minus 2 log base 2 of x equals to 3. So I get log base 2 of y plus 1 minus 2 log base 2 of x squared equals to 3. So I get log base 2 of y plus 1 divided by x squared equals to 3. So I get y plus 1 by x squared equals to 2 to the power 3, which is 8. And then I get y plus 1 equals to 8x squared. So I get y equals to 8x squared minus 1. This is equation 1. Moving on, I have another expression. Log base 2 of x plus 2 equals to 2 plus log base 2 of y. Again, break all the logarithmic terms to the exact one side, and then I will be able to deal with it. 2. So therefore, we get log base 2 of x plus 2 minus y divided by y equals to 2. X plus 2 by y equals to 4. So I get x plus 2 equals to 4. No, x plus 2 by 4 equals to y. So therefore, this thing equals to that. So 8x squared minus 1 equals to x plus 2 by 4. Okay. It told me to find out this, right? X cubed minus 6x squared plus 32 minus 32. Wait, is it going to be plus, right? It is plus. So if this is taken there, it's going to be plus. So it's actually going to be x squared into y plus 1. So actually, the following is going to happen. So therefore, now we can say that it's actually going to be the following. It is going to be y plus 1, no, y equals to 8 by x squared minus 1. If that's the case, we save this, otherwise I'm going to be at a huge risk. Okay, so now it's going to be 8 by x squared minus 1. So if that's the case, I can say this is going to be 8 minus x squared equals to x cubed plus 2x squared by 4. So I get 32 minus 4x squared equals to x cubed plus 2x squared. Okay, we are good. So I get x cubed minus plus 2x squared plus 4x squared minus 32 equal to 0. So I get x cubed plus 6x squared minus 32 equal to 0. So as an addition, I'm just going to solve this for you, the roots of it. So it's unnecessary, I mean, in some cases, but in other cases, this is quite necessary because I also have to show you some consequences of the negative roots and whatnot on the logarithms and whatnot. So I'm going to deal with that. And yeah, so I'm going to solve this root. Now, clearly by looking at the equation alone, x equals to 1 or x equals to minus 1 is not going to be the root of them. So as a trial and error, I'm going to select, let's just select x equals to 2. If x equals to 2, we get 8 plus 4 and 6 is 24 minus 32 equal to 0. 32 minus 32 equal to 0. So x minus 2 is a factor. Now, either you can use the long division method or you can use the factorization method. I'm going to use the factorization method, which involves the case where you have to gap one line so that you can deal with the distributions here. Now, because the base here is 1x cubed, I can easily say that it's going to be x squared because that's going to be unchanged. The other things are going to be changed according to the additions and subtractions we do on throughout the expressions. So I'm going to expand this one. I get x cubed minus 2x squared. We have 6x squared, so we need to add 8x squared here, so we're going to get 6x squared. So we get plus 4x minus 8x. We don't have any 8x, so we add 8x minus 16. Wait, that's 8x. That's going to be 8x minus 16x plus 16x. You don't have any x here. Plus 16 minus 32 equal to 0. So we get x minus 2 x squared plus 8x plus 16. Okay, that's just your expression for x plus 4 whole square. So I have x minus 2 x plus 4 whole square equal to 0. Oh, there's actually then there's just two roots. X equals to 2, x equals to minus 4. However, let me just show you something. I'm I'm thinking that this minus 4 is not going to be the solution. Although this is not going to be a problem here because it doesn't talk about this thing right here. It just talks about finding the roots of this expression. It's not like solving that equation alone, right? So I don't think x equals to minus 4 or whatever it is going to be a problem here. So that's going to be the case. So it was a combination of your factor theorem and remainder theorem. So yeah, That's basically it for this video, and I'm going to see you in the next one. That's it.